Good evening, everyone. So we have last lecture of this discussion meeting. We have Professor Rahul Kumar Singh. He will be discussing CMC surfaces
and
graphs.
vice transfer function. Okay, so
Yeah, what do you?
thank you very much for the invitation. Okay, so the title of my talk is so basically I can say space light CMC surfaces of revolution in L3. L3 is three-dimensional Lorentz-Minkowski space, and then we have this Weierstrass P functions. We can also say we have, so that we will see elliptic curves also. So yeah, you can see there are two different things. One is like we have geometric objects, and then also, and on the other hand, we are going to see Weierstrass P functions. So in this talk, we will see that there is a kind of, you can say, there's a relation between when one thinks about the space like CMC, or in general, just talk about CMC surfaces of revolution in L3 or E3, there corresponds a family of Weierstrass P functions or elliptic curves. So this is one of the aim of this talk, to show such a connection, and then as a consequence we will also see this connection between these two objects will also show that some, like, which surfaces of revolutions are going to be algebraic. So basically the question we would like to answer about the algebraicity of a CMC surface of revolution. So let me begin with some defining what is. So I will define all these things which are here, like Weierstrass P function, elliptic curves, and what is the meaning of saying when I say a surface is algebraic. Okay, and then then we will see what is the connection. Okay, so let me begin with this. So let me first define what is an algebraic surface we mean when I say we have an algebraic surface. So one can define a surface in E3. So E3 is, it's a usual or you can talk about, in general one can define in or L3 also. So L3 is simply, you can just do a minus sign here, and so L3 is simply R3 with this the metric which has one minus signature, and E3 is simply this. So one can define this as we say a surface in E3 is algebraic if let me just see if we can write S as, if we can see this as a zero set of some polynomial on R3. So what it says, so it is all so this is, so whenever I say a surface is in R3 is algebraic, I mean that if I am going to see that surface as a zero set of some polynomial. So this is the definition. So now once you have a surface in R3, we can also, if your surface is described like this, we can define its regularity, or when can we say it is a regular surface. So so we will say the surface S is regular if we compute the gradient of this polynomial. So any such surface, we will say it is an algebraic, regular surface if the gradient of this polynomial is non-zero at every point of this. For example, you can think of many examples. So for example, you have a sphere, cylinder, there are many examples. Okay, so this is the definition of a algebraic surface. But in this talk, what we are interested in, knowing when you have your surface, if your surface is having mean curvature non-zero constant. So h is a constant here, which is non-zero. So if it is non-zero, we say it's such a surface CMC. So we are interested in like in a particular class of surfaces in L3, and we would like to know out of like in that class which surfaces are algebraic. So let me first explain my problem, what is my problem, and then I will tell you about what development has been made in Euclidean setting. So let me first write for my problem. So the question I will be looking in that, suppose in the class of space like CMC surfaces of revolution in L3, we will show only, so I will say what is a space like cylinders and standard hyperboloids So this is so when I say like there is a connection between these objects, Weierstrass P functions and CMC surfaces of revolution. So yeah, so that connection will answer this. So now the first thing like we should know, okay, do we know all the CMC surfaces of revolution in L3? So the answer is yes. Yeah, so this is the question which I am interested. So I will show how to do this using this connection. But before that, now let me tell you what is known in E3. So yeah, so in Euclidean space, if you try to think of like examples of surfaces of revolution which having constant mean curvature, which are also algebraic, the two examples immediately comes to mind is one is this sphere. If you just write this S2, so S2 is simply so if I write this as, let's say, h squared, so we will say that this sphere is an example of a constant mean curvature surface, non-zero constant mean curvature surface, having constant mean curvature h, and this surface, as you can see, that this is algebraic. Why this is algebraic? Because we can define a polynomial in this case. Okay, since I am writing, okay, not S2, some circle. So this is, yeah, if I define. You can define it like this. And then we can see that for this polynomial, if you look at the zero set of this polynomial, this gives you this surface. And also you can check the gradient for every point on this S2 is non-zero, so anyway, we know it's a regular surface. So S2 is an example of a surface which is algebraic, having constant mean curvature. And the next example is any right circular cylinder. So you can think of this cylinder as having base, let's say if this is having, so you can write it like this. So this tells you that this cylinder is based on this circle, and this circle is in some xy plane. So the cylinder is also, so in this case also you can define another P, which is, and then you see that cylinder can also be seen as a zero set of this polynomial. And this cylinder is also an example of a algebraic surface. Now, so of course the question is, I am just showing you two examples of CMC surfaces in R3 or let's say Euclidean space which are algebraic. Are there other examples? So this was the question. Of course, so when I say are there other examples, I am not restricting myself to this class of some particular class. So for example, here you see I'm just interested, I'm going to talk about just a space like CMC surfaces of revolution. Means those surfaces in L3 which are also revolution surfaces. But here, one thing to note here, if you think about this sphere, so you can think of any sphere as, you know, surface of revolution. Right? You can take half semicircle and then you can kind of, so suppose if it's a z-axis and let's say this is x-axis and then you have y, you can kind of revolve it around this and then you will see you will get a sphere. So a sphere is an example of a CMC surface which is also a surface of revolution. The same is true for cylinder. For a cylinder also you can just take a line parallel to this and then you just rotate it about this axis. So these two examples which we see in E3, they are algebraic and they also happens to be surfaces of revolution. What more we know about this? We know that these two surfaces are regular also, according to this definition, whatever definition I have given. So these two examples are two examples which are, I can say they are regular algebraic CMC surfaces. And it so happens like these two examples belongs to this class of surface. They are surfaces of revolution. Now the question is, are there any other? Let's not restrict to this surface of revolution. What are other examples? So as it turns out, so there is a result due to Dockermo and Barbosa. They showed like if you are looking for regular algebraic CMC surfaces in R3 or Euclidean space, then there are just these two examples. So yeah, so this is due to Barbosa, Lucas Barbosa. This is, I think, in the year 2016. They showed that spheres and right circular cylinders are the only examples of regular So there are just these two examples. So this is when h is a non-zero constant. So these are the only two examples. So you cannot find any other example. This is what it says. And now you can see those two examples, they also happens to be surfaces of revolution. Okay, and they could prove this. So the main idea behind this proof that there exists some structure theorem for CMC surfaces. A structure theorem means there's a theorem which tells you that about if you take a general CMC surface, how it ends will behave. So you know all about its behavior of its ends, and they use that theorem to prove this thing. And of course, there are some other things. So using that particular theorem, they could prove this. Now so this is one thing. So this is about H non-zero. So of course now one also would like to see what happens for H equal to 0. So that means when you have a zero mean curvature, or when you have for instance, minimal surfaces. Do we have examples of minimal surfaces which are algebraic? And the answer is of course yes. The simplest example is the example of a plane, right? If you think of a plane in R3, so any plane, a general plane in R3 can be define, yeah, not ABC are not simultaneously 0. So this defines a plane in R3, and then you know that you can define a polynomial, degree 1 polynomial, and the 0 set of this polynomial is a plane. So for h is equal to 0, there is this one example. Now, are there any other example? So as it turns out, when you are just thinking of minimal surfaces being algebraic, there are many examples. So another example you can find is of this n-apple surface. So n-apple surface is also an example of a minimal surface, and yeah, okay. Let me just yeah. So when you look at this definition, so we can also define the degree of a surface. So degree of a surface is the least integer power of that polynomial which satisfy, whose 0 set is that surface. So so I can say now the degree of plane is 1, because this is just a, and if you try to see what is the polynomial, of course this is a polynomial xyz and having degree, so there will be degree 9 polynomial. So there are other examples also, not only these, okay. So this is one and this is another, and then there are many more. So one can, if you are interested in looking at what are other examples, so there is a very classic book by on minimal surface by Nischay. So the title is Lectures on Minimal Surfaces. So there you can see many examples. Huh? This example? Yeah, these are algebraic. So I am saying, I am referring to this book to look for some more examples of minimal surfaces which are algebraic. But now if you try to, if you have like seen previous lectures, so there, I think Professor Soichi Fujimori have shown the picture of this n-apple surface, and you could see that this surface has self-intersection. Right, they at some point in space they cross each other. So as it turns out, if you have this, so according to our definition, this, since this is a self-intersection, this can be regular if you are writing this as a 0 set of this polynomial. So this example is, although it's a algebraic minimal surface, but this is non-regular in our sense. So it's a non-regular. It's a not regular surface. And of course, yeah, this is regular, but this is non-regular. Okay, so now the question is, what are then regular examples when you? Huh? I do not know. I think there are no such. Let me tell you. So I think no, but I do not know why. What is the reason? But there are many examples like of higher degree, but I'm not sure. Let me not say that I. So yeah. Okay, so yeah, so the now in the same paper, this paper by this Barbosa and Docomo, they also answered for this question. So they answered this, asked the same question. So then, okay, what are all regular algebraic minimal surfaces? Let's say, and the answer is just one. So they also obtained this, that when H is 0, plane is the only example of minimal surface which is algebraic. Okay, so this is also one of their results in that same paper. So in this paper, So after showing this, they also showed this. So like you can see, when you have a non-zero constant mean curvature, there are two examples at least. But when it's you're just saying zero mean curvature, you have just one regular example. So now when I'm saying that you can find many more examples of algebraic minimal surfaces in R3, let's say Euclidean space, you're going to see, you're not going to see regular examples. They will have some kind of self-intersection sort of things, okay? So now, so of course, in this paper, they do not like talk about do we have examples of, non-zero CMC algebraic surfaces, which are also, let's not put the assumption of regularity. Do we have such examples? So yeah, nothing has been said. And I also do not see if there are examples for in the CMC surfaces case. Like for example here, when h is equal to 0, you have at least n plus. So this is for when you are putting the assumption of regularity. But suppose if I say non-regular, what are other examples? So I do not know any example of a of an algebraic surface, non-zero constant mean curvature, and which is also non-regular. Okay, so yeah, so that is one thing. And now let me just also tell you. So of course I am going to show you this. I will prove this through this. Like I will show you in this class of CMC surface of revolution only what I said. The standard hyperboloids and space-like cylinders are going to be algebraic. But what I will also show that in this class, I will show you how the surfaces appear, CMC surfaces appear in this class. I know the geometry, how the geometry looks like. We will be able to tell about some of the surfaces, which are, which are again CMC surfaces of revolution, non-regular, and they are not algebraic in some sense. So I am also going to say about non-algebraic, so some CMC surfaces cannot be algebraic. And the same idea, the same thing one can adapt in the Euclidean space setting to answer, you can say the partially, even not partially, I don't know what to say, but it's a very small class. It's just this result is in whole E3. But I am just restricting a class of surface of revolution. So for example, from their method, you cannot say, suppose if I ask you, there is some example. If I give you some CMC surface, can you say if it is algebraic or non-algebraic? So at least I can say in that class, there are some examples which are not algebraic. Okay, so okay, I think. Sorry? Yeah, so yeah, analogously, we do have examples of maximal surface, you can say, when h is equal to 0, which are algebraic. And there are many, because there is a duality. So again, yeah. Yeah, so that, yeah. Okay, so now let me, yeah, so before I begin, let me tell you at least if you try to think of what are all not space-like, CMC surfaces of revolution E3. Do we have a characterization? So yeah, do we have characterization? So again, this is a result due to, in fact, this was also known due to Delannoy. So there is something called Delannoy surfaces. So Delannoy surfaces are when you have a, so okay, so let me just, so I'm just going to tell you, what are all CMC surfaces of revolution in E3. So you have a line, you take a line which is parallel to one of its axes in the space, and then you just rotate it about this axis. And of course, we will assume it is not intersecting, then this, we know this will generate a cylinder. Then the next you can it looks like sine, but it's not sine, a curve like this. And of course, you will see, and this, so there are names for this. So this is like a line. So this curve has a name, undulary. And then you see half semicircles like this, and then you have. So it's like, you know, why I'm drawing these curves, because you will know a surface of revolution if you know its generating curve. So it's like what I have drawn is just the generating curves of those surfaces of revolution whose like mean curvature is constant, non-zero constant. So now you know that this will give you a cylinder. This, when now you can imagine if you like revolve it around like one of its axes, then you will get some shape. So that shape is what we call unduloid. And you know that this, you will see the spheres. And when you revolve this, you will, of course, you will see that you will get a surface having many self-intersection, and this is what we call the nodoids, and this is nodary. Okay. So what I have shown you just like 4 topologically kind of different, I should not say topologically, it's the same. Anyway, so these 4 kind of curves you can see here, and now there's a, when I'm saying there is a classification of the CMC surfaces of revolution in R3 in terms of its parametrization. Means you can, not only you will know what are all surfaces of revolution having constant mean curvature in E3, and you will also be able to provide a parametrization. And that parametrization is, you know, it's not just as, you won't get as one parameter, you will get a family of parametrization, which will be, that family will be parameterized by some parameter, let's say B, which is allowed to vary between 0 till infinity. You can take B to be negative also, but that is something you're not going to see something new. So what I'm saying now, you see this parameter B. So for each B, because each B will give you a parametrization for some curves in this family. Okay, and when you rotate, you will have a surface of revolution. So for instance, if you look at this picture, so the B equal to 0, so I won't write this parametrization for this, but I will say how we can obtain the same kind of parametrization in Norman-Minkowski space, and then maybe at the end I will show you what is that parametrization. So this is, okay, anyway, this result is due to this Kei Kenmotsu, Japanese mathematician, I think around maybe 83. So he sort of like given a like classification, he characterized all surfaces of revolution in R3. So this corresponds to B equal to 0, and this corresponds to B equal to 1. And for anything between 0 and 1, you will have, when B is between 0 and 1, you will have curves like this. So you are going to get unduloids when B is varying between, including 0 and 1. No, not including. So this reason is for. And here, this is all such. So at least there is such a there exists a characterization of surfaces of revolution, CMC surfaces of revolution in R3, and that is the key. So that characterization, because I am saying that characterization is also giving you a parametrization. You also know that what is the exact parametrization. Of course, we have a general parametrization for a surface of revolution, right? Using cosine theta, sine theta, because you can write. But what are the coordinates of when I'm saying a general parametrization? That means I would like to know. Suppose if I'm drawing this in xz plane, so you know. Okay, so so suppose this is the, let's say the suppose your curve is a regular curve, so you can have this parametrization. So in that paper, what the Kenmotsu has obtained, he has obtained a formula for this x of s in terms of this parameter B, x of s and z of s. And then you know, if you revolve it around, let's say, z-axis, you have and then you can put those, so that you will see that everything, so there is a parameter b there. And this parameterization is crucial because that parameterization, we are going to use such a parameterization, which of course I will show. So this is the result due to Kenmotsu, but later on, like again, there's some, yeah, maybe I will talk about it later on. So yeah, so what I'm saying, this parameterization is very crucial because this will help us, this type of parameterization will help us like relate the CMC surface of revolution to what we call elliptic curves and Weierstrass P functions. So that is going to be important. Okay, so before I say something more, I will just outline, give you a idea of the proof, means I will just write steps which will give me the ultimately the result, and then I will explain everything. So I think I removed, okay, anyway, I removed the thing like what, so I'm writing the idea of the proof for that result, like how will I show that in the when you consider the space-like surfaces of revolution in L3, the standard hyperboloids and the space-like cylinders are the only examples. One more thing, there is a difference, like when you want to consider the surfaces of revolution in R3, you know, because when you have L3, let's say, so different x's will have different nature, like causality. Like for example, if the metric is dx square plus dy square minus dz square, then the z-axis is a time-like axis. So if you are rotating your curve around a time-like axis, you will have a different set of parameterization. And if you are rotating your curve around a space-like axis, let's say for example x-axis, you will have a different set of parameterization. So you will see some different kind of, so you will have two different kind of families, or in general maybe three if you have. So, but in my talk, what I am going to show you, I am just going to show you, I will consider mainly the space-like surfaces of revolution around z-axis and prove the result, obtain the result. The same thing can be done for space-like axis also, which I will not show, but I will just state. So that's, yeah, and all my surfaces are going to be space-like. That means the induced metric is Riemannian, such a surface. So okay, so what is the idea of the proof? So how I am going to show this? Yeah, one more thing. One can think about, you know, if just ask a similar question for in general L3, that what are all regular, let's say, algebraic surfaces in L3, but and try to adapt their method, what they used. But that cannot be done because what they used to, in order to prove such a result, they use that structure theorem, which is available for the CMC surfaces in Euclidean space, but I'm not aware of any such structure theorem in L3. So we cannot adapt such method and try to prove a similar result here. So instead, even though not about the full, but if you restrict to some class, we could say about the what are algebraic surfaces in that class, and not only that, we have one extra thing, like we could see that these new, some different things are appearing. So that is kind of interesting. So idea of the proof is, so first thing is to prove that there exists a Kenmotsu's type parameterization for space-like surfaces space-like CMC surfaces. Okay, CMC surfaces. I will write the parametrization. After doing this, the next step is to show that from that family, if you once you have such a parametrization, so for a given surface of revolution from this family, we will associate an elliptic curve And this one can do using this parameterization. Using the above parameterization. And once you see that you are getting an elliptic curve, I will define what is an elliptic curve in a moment, but let me. So then again, there is a result from number theory that it says that for every elliptic curve, so when I'm saying, so maybe elliptic curve means, when you study elliptic curves, you will see there are two types of elliptic curves. One can talk about, singular elliptic curves and non-singular, because there is one can associate a discriminant of elliptic curve, and depending on the nature of the discriminant, one can talk about non-singular and singular. So so the result is for every elliptic curve whose discriminant, I will say in a moment what is this, whose discriminant is non-zero. So you can think of kind of a smooth elliptic, if you know about elliptic curves, so they are kind of a smooth elliptic. So I think if you might have seen these pictures, kind of like this. So these all are elliptic curves. This is how they look like. They also have but when I'm saying smooth, that means non-zero. So you will see without any self-intersections. So these are not smooth, but still they are elliptic curves. So for every elliptic curve whose discriminant is non-zero, there exists a Weierstrass P function. And I can, if you want to see about this, of course there are many resources where you can find these stuffs, but one book you can look into is this L.C. Washington. This is a book, and the title is, I think title includes elliptic curve, cryptography, and some things. So so there is a book due to this. So you can find more about this relation. And the last is, so these are the steps which are involved in showing what I want to say. And the last thing we will claim, there is also, this is a fact, that a Weierstrass function, a Weierstrass P function, does not satisfy any algebraic relation. So now you can see. So let me tell you. So the way we are going to prove this by method of contradiction. So ultimately we will assume, okay, suppose what happens if it is algebraic, and then we will show that we will have some elliptic or Weierstrass P function which are satisfying an algebraic relation. So what is the meaning of saying algebra? So again, so what is known is this Weierstrass P functions are transcendental. So transcendental functions are those which do not satisfy any algebraic relation, means something kind of polynomial. So you cannot write a polynomial in P is equal to 0, that sort of. So it won't, this is a fact. But what we will show, if we assume that those surfaces are going to be algebraic, then we will reach a contradiction. We will show that the Weierstrass P function which we have obtained for that surface is violating this. Okay, so this is the whole idea. And so, okay, now let me just quickly. So now I will start with this. So let's start with so we will start with a curve. So this is an xyz plane. So remember, metric is dx square plus dy square minus dz squared, where we can assume that this condition is just to avoid that curve is not intersecting the axis about which we are rotating. This is, And then when you rotate this curve, when we rotate it about z-axis, which is a time-like axis, the corresponding surface of revolution will have this kind of thing. Okay, so this is when you revolve. So a surface of revolution in L3 about z-axis can be given this parametrization, and if you are revolving this about, let's say, x-axis, which is now a space-like axis, then you will see there is a different kind of, you will have hyperbolic sine theta. So you might be thinking why this thing appeared, but now if you think about, you can also think of the surfaces of revolutions, such surfaces which remains invariant in some kind of rigid motion of R3, and there's a matrix which, so you can, so now in L3, when you are thinking of surfaces of revolution about x-axis, there is a different kind of, so under that motion it will be remains invariant. So but anyway, this is the known general result. And yeah, now once you have this, we can, following Kenmotsu, that idea, we can write down, we can obtain a parametrization for surfaces of revolution whose mean curvature is non-zero constant. So following Kenmotsu, if we assume that we want H to be non-zero, we want, when we revolve it, we want a non-zero constant mean curvature surface. So in that case, we can obtain this parametrization. So this is your XS ZS. So T is just for that we are doing about time like axis, and the parametrization is given by 2H 2B cosine. This is how the x coordinate will be given by, and the y coordinate is 0. Hyperbolic cosine, and this is square root of so you might see this is square roots and then this, but all these things are well defined. There's no problem. These things are all going to be positive, so this is not an issue. So this is the so the Kenmotsu has also obtained a similar kind of parametrization for those curves. So now you see, so when you so this is the parametrization for these curves, like these kind of curves, one of these kind. Now when you vary this parameter b, you will see different kind of CMC surface of revolution. Now you can see what will be the parametrization for a space like CMC surfaces of revolution about z-axis. You just replace xs by this, so this will use. So now once you see this, yeah, now in 5 minutes I will just say briefly about this elliptic curves and Weierstrass P function, and then I will again come back to this. So what is in so elliptic curve can be so yeah, generally if you are trying to define an elliptic curve over a complex field, one can talk about elliptic curves over any field. So what is the meaning of this? So I'm just considering the elliptic curve over complex field over C. That means this is the, so it is an elliptic curve is simply set of all points which satisfy this equation. And then, yeah, so you can think about this. So we have this complex elliptic curves, and the discriminant is, let's write D. So for such a elliptic curve, the discriminant will be given by. Now, if D is non-zero, not equal to 0, you will say that this elliptic curve is a smooth elliptic curve, or it is a non-singular. And if D is 0, then we are going to see the singular. Okay, so yeah, this is. Now, what is a Weierstrass P function? So you know, Weierstrass P functions as such, they are doubly periodic functions defined on complex plane. They are, of course, they are meromorphic functions, and so you can think of Weierstrass. So in complex plane, you can, you know, you given a lattice means you just consider some set of lines and choose integral points. So and then you can have a Weierstrass function defined on this, and for that Weierstrass function, which I am saying doubly periodic, so there will be, so that means there will be some fundamental domain associated to that Weierstrass P function, and then so once you see a lattice like this, you know, see if you quotient it by a lattice just made out of this, you know, a lattice is what? This is, let me just. It is, yeah, any lattice in complex plane is simply, so omega 1 and omega 2 are two linearly independent complex numbers, non-zero complex number, then you take, so you're just going to see the integral multiples of this spread all over this. So Weierstrass function, you can think of, so maybe I think I won't define it here because, but I will just say, because that is, we are not going to use anything, any properties except few which I have already stated there. So I will just say, so Weierstrass function one can think of, it is a doubly periodic function defined on complex plane. So since it is a doubly periodic, you can also think of it as defined on a torus, right? Because so there is a square in which, you know, when you restrict to some square, it will be like a bijection. So there is an identification of such a square, and if when it gets identified, you will see a torus. Yeah, so that is Weierstrass P function, and yeah, so and then so this is so there is a result fact which I stated here, that if you have an elliptic curve whose discriminant is non-zero, there is a Weierstrass P function, and not only you have a Weierstrass P function, and that Weierstrass P function will satisfy this equation. So there is a Weierstrass P function, and this P function will satisfy, let's say, let me just write it here, that, of course, this is like, so you know, when you have Weierstrass P function, you can also talk about this derivative. So the Weierstrass P function and its derivative will satisfy this equation, the P prime square, and this is equal to this 4P cube minus Z2P. So it tells you, you know, that you can have a parametrization for such an elliptic curve using the Weierstrass function and its derivative. So Weierstrass function, yeah. So whenever you have a non-singular elliptic curve, you will always see that you have a Weierstrass P function which will satisfy this. So these things we are going to use, and yeah. Okay, so now let's go back to this. So I will show you, that how we are going to associate an elliptic curve. And the thing which is important to us is, we will just focus on this part, this integral. So see, this integral is just one of the coordinate expression for the coordinates of this curve ZS. So we will focus on this, and from here we will try to bring in elliptic curve from this equation. So this involves a series of, to bring in some elliptic curve from this involves a series of change of variables. Like we have to apply some change of variables. So I will just tell you. So yeah, there's few change of variables one has to do in order to arrive at something like a. So we ultimately we want to see an equation like this from this. So what we are going to do now, so here in this expression, we will first do a change of variable, or a kind of, we will say that let's replace this hyperbolic cosine 2ht by a new variable, let's call it u. So when we will do this, so let me write you the ultimate expression. When you do that change of variable, that you write u to be ht, then what we are going to see is this. We will see. So this thing will turn into 1 by 2h. Yeah, I think it's. And then we will make one more change of variable, and in this expression now we will introduce a new variable. Let's replace w by u plus c. Now this c is a constant which we will choose later on. So we can just, for any constant, we can just replace, let's say u by w minus c. So writing w as u plus c. So if you put this thing here, there will be some change of variable, and what you will see is this. So ZS will, which we started there, will look like this is ZS. It will look like 1 by 2h, 1 plus c. Now you see L, M, N, R. Now this L is something which depends on this. Okay, let me just. So L is where they are the expression which depends on B, that parameter B. L is this B square plus 1 plus 2BC. Let's see. Yeah, and similarly, so for M and N. So what I'm saying, L, M, and N are going to be, okay, yeah, one more thing here. So you see, in this, you have U square and U cube. But in order to like replace this U square here, I need to do something. So yeah, so this, when I'm doing this change of variable here, so the C will be, we will choose C to be, now you can see, because I do not want this square term, because I want something like this elliptic curve equation. So I will choose C to be simply B, so that this becomes 0. So I will choose, yeah. me. Okay. I'm not written what exactly C is, but anyway, so what I'm saying, in this process, we can choose a value of C here, put a value of C so that this thing can be removed. And yeah, after, so we can, I don't know, I not, maybe C is, anyway, so yeah. So this step is to just get rid of the CU square term. Like we can choose C so that this thing can be removed, and then you will have again new set of variable W. So this is how it looks like. Now if you look at this, so this is now resembling this equation. Not exactly like this. So again, you can further do if you just want to write exactly like this so that we can write the discriminant like this. So you can do one more change of variable now to, so okay, first what you do, let me just call it this. So this is going to be positive always because this is in the parameterization. We can write this to be, this whole thing to be V square is equal to L plus MW plus MWQ. So yeah, now this is like almost like this, but now if you want to see this into that form, you can further do this change. Let's replace W by this, and then when you do this, you will see this is and now you can see that this is like a elliptic curve. Of course, you have now this real thing, which are also complex. But so what we have done for each such curve, which we know that this is one of the component, we have associated a elliptic curve. But now we do not know what is this elliptic curve. Is it singular or non-singular? So uh, as it turns out, so this is so this is the first stage, like where by looking, so we can say now, because now these are what, these curves will generate the CMC surfaces of revolution. So this for each value of B, because see, you look at this M, L and N, they all ultimately depend on B only. The choice of C will also depend on B. So everything depends on B. So for every, so when you change B here, that means you are seeing some surface of revolution, CMC surface of revolution for that given B. So that means you are seeing one of those curves which I drew in this for Euclidean plane. So yeah, so for each such surface of revolution, we can associate an elliptic curve, this facet. And how this is coming? This is coming from this coordinate. So there is a kind of association, like you start with a, the a CMC surface of revolution corresponding to a parameter B, you're going to see a elliptic curve. So for each B, you have a elliptic curve. So it's like, this class of CMC surface of revolution about time, like axis, it identifies, you can say, a subclass of elliptic curves, because for each B, you have an elliptic curve. Of course, the next we will see when they are going to be singular or non-singular. So this is one connection. So here you see the appearance of this elliptic curve, and I can continue for 15. Is it okay now if I continue? Yeah. So these are elliptic curves. Now we have this theorem which says a space like CMC So in this case also, this B parameter which you see here, this can vary in this interval. So this theorem says now that this space, if you're looking into the class of CMC surfaces of revolution in L3 about z-axis, that means time like axis, then for B between 0 is not included and 1 is also not included. For each such B, one can show that they're not going to be algebraic. But what happens for B equal to 0 and 1 case? So for B equal to 0 and 1 case, so we have, so I will just say what is, yeah, so when B is 0, so you can see this when B is 0. So from this, you can check that you will get Z equal to 1 by 2H. So this line, which is parallel to this Z-axis, and when you will revolve it around Z-axis, this will generate a space-like cylinder. So this is the equation of this is how the space-like cylinder will look like. And when, oh, sorry, I'm sorry, this, no, this is Z. Actually, yeah, you will see, so in this case, what you are going to see, you are going to see an imaginary cylinder. So yeah, so let me, I'm sorry. This you will see, you will get something like x square plus y square is equal to minus 1 by 4h. Now you can see there is no such xy which satisfies. So this is a kind of course, this doesn't exist, but anyway, this is an imaginary space-like cylinder, and this will generate the standard hyperboloid. Yeah. So at least when you are considering this surfaces of revolution about time-like axis, the cylinder which you are seeing is an imaginary cylinder, and this is the, this is corresponding to sphere. So what you are going to see, this hyperboloid, standard hyperboloid, which are 2, where with this condition x positive. Now when you, so I have not written down, so when you revolve this, we again have something like this in this case also, and in that case, when you will see compute this for B equal to 0 in that family, you are going to get this hyperbolic cylinder, which is given by so this is how the space-like cylinder about a space-like X looks like. So it's not your right circular cylinder; it's a hyperbolic cylinder, and in that case, when you, so in this case, you will see this equation. So this is the circle in Lorentz-Minkowski space about space like x-axis, and when you revolve it, you will get again the standard hyperboloid, the same equation, but now with the z is positive. So in both the cases, you see, and now you can see that for b equal to 0, 1, they are all already, you can see they're algebraic. So these are, and for when b is not, so this is clear. So so this theorem says that for b in 0, open 0 infinity, minus 1, all are, nothing is algebraic. So algebraic we already seen for b equal to 0, we are getting here, these are the surfaces. And for 1, what happens? We will see. So 1, when you take b equal to 1, this b equal to 1 corresponds to a singular elliptic curve. So the next thing we are going to do, so now we see the elliptic curve there. So for this elliptic curve, the discriminant, if we try to compute its discriminant, so it will appear in terms of b, and the discriminant is so the discriminant in this case will have, you will get this 2 times, so this is the discriminant. So this is after like lots of simplification. So because you can write down the discriminant expression from this, and when you simplify this, this is what you will see ultimately. And you can see when b is equal to 1, and b is equal to 1, we know it gives you a cylinder. So but for b equal to 1, this discriminant is 0. So it's like, in this family, this cylinder corresponds to a singular elliptic curve. And for rest of them, and for, of course, b equal to 0, nothing is said. So in this family, so what you see, so in this family, of course, so this CMC surfaces of revolution identifies some subclass of elliptic curves. In that family, there's one singular curve which comes from this cylinder. So this is, and so this is the theorem, and the idea is, I will just say, try to interval time. So this. So this is So in terms of so this was like d was minus. So you have to evaluate this expression, and when you compute this, because as I said, L, M, N, everything depends on B ultimately. So when you simplify this, I have not written down the expression for M and N, but I will. So this is what you see, and so this is not 0 except for B equal to 1. And now, if you try to compare with this, so this there is this again a fact which I mentioned here, that for every such non-singular elliptic curve, there exists a Weierstrass P function which will satisfy this. So now what we can say, that when this discriminant is non-zero, we will have a Weierstrass P function. There exists a Weierstrass P function, so that this P function will satisfy this, or maybe let me just think I have not one more result I have to state that just quickly. Yeah, so the result which I am referring to is, which says, so is this result, this is a fact, for every non-singular elliptic curve, the result is this. There exists a lattice L in C, because once you know a lattice, you know you will have a Weierstrass P function defined on this lattice, with respect to this lattice, and corresponding to this L, there exists a Weierstrass P function which satisfy So from that elliptic curve, because we know that this elliptic curves we are getting they are non-singular. So for each such non-singular elliptic curves, so I am writing a result. So there is this fact that there is for every non-singular elliptic curve, there is a lattice L in C. Whenever you have a lattice, you can define a Weierstrass P function corresponding to this lattice, and that Weierstrass P function and its derivative will satisfy this equation. So I am writing this Z tilde to denote the complex coordinate in Z, because Z is already appeared in this XYZ. So this Z tilde is the complex number. So you see, so now we have this relation. So now once we see this relation, yeah, so I think I won't write the details. I will just tell you idea and how we are let me just. Yeah. So so now, yeah, one more thing is this, that once you see this relation, you can further, you can further go like you can also write differentiate this once more, like so if with respect to Z tilde, so you will see this. So when you differentiate it, what you will see, you will have 2 P prime and P double prime, and here you will have P prime, which is common here, but then you would like to cancel this P prime. But that one can always do by just choosing some neighborhood of some point Z tilde small enough so that in that neighborhood P prime Z tilde is not equal to 0. If it is not equal to 0, you can have this relation. From this you will have this P double prime Z tilde 2 times 12. So now the overall idea is to use these relations and somehow like take these equations, these relations into these equations. So I am now skipping a lot of things, and what you will see ultimately is that still, yeah. I think there are many more things. I will just try to, I will try to wrap it. Yeah. Okay. So, yeah. So once we get this, and yeah, one more fact I will just say about surface of revolution. If you have a surface of revolution in, let's say R3 or L3, and of course in our case it is about Z axis, then any surface of revolution can be described as a zero set of this polynomial, or it can be, yeah. So this is something which is true for surface of revolution, that any surface of revolution, of course in our case also because we are revolving it around z-axis, so this will have this form. And then what we will say, because we already know that the surface of revolution will look like this, means it will be described by the zero set of this polynomial. The only thing which we want to make sure about this, what is the nature of this R of z? We want to say this R of z cannot be a polynomial, because because any surface of revolution can be represented by this equation, zero set of this equation. If R of z is a polynomial, then anyway we are seeing an algebraic thing. So the thing we want to claim here, that R of z cannot be polynomial, because if R of z is polynomial, then you see that everything is a polynomial. So we would like to say that this is not a polynomial. So in contrary, what we will assume, we will start assuming with the assumption that this R of z is, let's say if it is a polynomial for all such b, then what happens if we assume this, we will ultimately see that this p will appear, because we can relate this to this parametrization, and we will see that this p will satisfy some algebraic relation. So yeah, I think I have, sorry, I thought I will manage it, but it looks like it will take more time. Yeah, sorry, okay, anyway, I can just write the reference if anyone likes to, because details are there. I'm sorry for that, because I thought I will manage it in 1.5 hours, but it looks like, but anyway, I will just, yeah, so the archive number, this is, so there are 2 versions, so this is the latest. So yeah, maybe you can go and check on this, and if you have any questions, you can always comment or write to me. I'm sorry, so because I have not shown you how this algebraic, because I think if I will do all those things, it will take 1 more hour. Sorry. Yeah.
Any questions?
Thank you.
Yeah.
Yeah. Do you, since you mentioned about this theorem of Ducarmo and Barbosa for Euclidean 3 space, is there an analog for Lorentzian space?
So there is, so that's what I said also, because they used something, of course one can ask a similar question in Lorentz-Minkowski space, 3-dimensional Lorentz-Minkowski space, but if one wants to mimic their idea or the method, one cannot do that, because they used something called a structure theorem. There is a structure theorem which is there for CMC surfaces in Euclidean space, but I'm not aware if any such theorem is there. So yeah, so we cannot think of, but yeah, there are generalization of this question in higher dimension. Like one can ask about in Rn what are all CMC hypersurfaces which are algebraic. So as it turns out, so people are there's some progress in this direction, and it looks like that the higher dimensional sphere and cylinders are going to be the only regulars.
Questions? Okay, so we thank speaker once again.